Hello, and thank you for listening to this presentation. The title is Implementation of Kalman Filtering for Differential Algebraic Equations. Differential algebraic equations arise in several applications, including chemical and physical processes, and as a result of discretizing parabolic elliptic partial differential equations. Coupled differential and algebraic equations present computational challenges. One issue in differential algebraic equations, particularly nonlinear, is their estimation. For nonlinear ordinary differential equations, the extended Kalman filters and unscented Kalman filters are popular. Often, the differential algebraic equation can be converted into an ordinary differential equation, and then a standard method for ordinary differential equations, such as extended Kalman filter or unscented Kalman filter, is used. Converting a differential algebraic equation to a system of ordinary differential equations, however, presents its own set of problems, such as the introduction of numerical errors, and estimates may not satisfy algebraic constraints. The extended Kalman filter and unscented Kalman filter have been generalized in prior works to a class of differential algebraic equations. Without conversion of the differential algebraic equation to a system of ordinary differential equations. The developed algorithms were implemented on several examples, but no comparison to existing approaches was provided. A differential algebraic equation is an ordinary differential equation combined with an algebraic constraint. A differential algebraic equation is semi-explicit if it is of the form in equation 1. Equation 1a denotes the differential part, and equation 1b is the algebraic constraint. X subscript d denotes the differential state, and X subscript a denotes the algebraic state. The general form of the differential algebraic equation is given by equation 2, where the Jacobian of f, taken with respect to the derivative of x, x dot, is singular. If it was non-singular, we would have an ordinary differential equation. A semi-explicit differential algebraic equation is index 1 if the Jacobian of the algebraic constraint taken with respect to the algebraic variable is non-singular. If a semi-explicit differential algebraic equation is index 1, then by the implicit function theorem, for every time t and differential state x subscript d, there exists x subscript a such that the algebraic constraint is satisfied. Thus, such systems are well posed. It is possible to convert a semi-explicit index 1 differential algebraic equation into an ordinary differential equation. Differentiating the algebraic constraint with respect to time allows us to replace the algebraic constraint with the differential equation in equation 5. In 2001, a modified extended Kalman filter was developed for semi-explicit index 1 differential algebraic equations. In this approach, the algebraic state estimates were computed using only the updated differential state estimates and did not use the prior algebraic state estimates, nor did they use the information made available through measurements of the algebraic states. In 2010, a new modified extended Kalman filter was introduced which eliminated these disadvantages. This extended Kalman filter is utilized in this work. It may be convenient to convert a differential algebraic equation to an ordinary differential equation. However, there are a couple of reasons for not doing so. Converting a differential algebraic equation to an ordinary differential equation can introduce numerical errors when simulated with an ordinary differential equation solver. Additionally, the estimates produced by the state estimators may not satisfy the algebraic constraints, leading to incorrect initialization in the subsequent time step. Therefore, it may be necessary to use a Kalman filter directly on the differential algebraic equation. Similarly to the common extended Kalman filter, when applying the extended Kalman filter on a differential algebraic equation, the initial state is propagated forward, as is the covariance using a linearized model. After which the Kalman gain is calculated, the differential states are updated, then the algebraic constraint is solved to produce the updated algebraic states. Applying the unscented Kalman filter on a differential algebraic equation can be computationally expensive. Each sigma point has a differential and an algebraic part. The differential part is calculated in the standard way, then the algebraic constraint is solved to obtain the algebraic part. This has to be done for every sigma point and for both steps in each iteration of the unscented Kalman filter. Here we have an example, a model of a mixing tank with three states: concentration, represented by the lowercase letter c, temperature, represented by the uppercase letter T, and reaction rate per unit volume, represented by the lowercase letter r. The reaction rate per unit volume is the only algebraic variable in this model. This system of equations is semi-explicit. Equations 6a and 6b encompass the differential parts, and equation 6c is the algebraic constraint. The derivative of the algebraic constraint, taken with respect to the algebraic variable r, is equal to 1. Thus, this system is index 1. The results of estimating this model using the measurement of the differential variable temperature with these four different filters is shown here. The solid blue line labeled ODE EKF is the relative error of the estimate provided by converting the differential algebraic equation into a system of ordinary differential equations and applying the extended Kalman filter. Similarly, with the dashed dot yellow line labeled ODE UKF, but applying the unscented Kalman filter. The dashed orange line labeled DAE EKF is the relative error of the estimate provided by applying the Kalman filter on the differential algebraic equation. Similarly, with the dotted purple line labeled DAE UKF, but applying the unscented Kalman filter. All estimators perform with roughly the same accuracy in estimating state 2, but the estimators applied on the differential algebraic equation perform better in estimating states 1 and 3. For state 3, the ordinary differential equation estimates converge quicker, but eventually provide an estimate with a larger error. The extended Kalman filter applied on the original differential algebraic equation provides a more accurate estimate, but has a computation time that is 37% slower compared to the extended Kalman filter applied on the system of ordinary differential equations. The unscented Kalman filter applied on the original differential algebraic equation provides a more accurate estimate, but has a computation time that is 25% slower when compared to the unscented Kalman filter applied on the system of ordinary differential equations. The extended Kalman filter applied on the original differential algebraic equation provides a more accurate estimate, but has a computation time that is 77% faster when compared to the unscented Kalman filter applied on the system of ordinary differential equations. A similar simulation was done with measurement of the algebraic state, the reaction rate per unit volume. The results are shown here. For state 1, the differential algebraic equation estimates converge quicker and are more accurate. For states 2 and 3, The ordinary differential equation estimates converge quicker, but the differential algebraic equation estimates are more accurate. The computation times were similar to those of the previous simulation. In this work, we compared two approaches for Kalman filtering of differential algebraic equations: conversion to an ordinary differential equation prior to estimation versus estimation directly with the differential algebraic equation. In general, extended and unscented Kalman filters applied on the original differential algebraic equation provided a more accurate estimate but at a greater computation time, when compared to applying the Kalman filters on the system of ordinary differential equations for two semi-explicit index 1 models. One of these models was discussed here, the mixing tank. For the other one, the results were similar. The comparisons were done for measurement of a differential state and for measurement of an algebraic state. Overall, the extended Kalman filter applied on the original differential algebraic equation performed the best when considering both accuracy and computation time. This work was focused on the implementation of Kalman filtering on semi-explicit index 1 differential algebraic equations. Future work includes Kalman filtering of index 2 differential algebraic equations and on handling the situation where the index depends on the state. Thank you for your attention.